Hi everyone, I'm very excited to share our recent work on model compression today. ICQuant index coding enables low-bit language model quantization. As we all know, large language models are powerful, but too large, usually with billions of parameters. For example, a 32 billion parameter model in full precision can take up to 128 gigabytes just to store the weights. And this large memory overhead makes it really hard to be deployed, especially on edge devices. Also, for edge applications, the inference are usually memory-bound, which means just moving those weights around the memory can dominate the latency. So weight quantization comes as a practical solution, where we store weights in lower number of bits. For example, from 32-bit to 4-bit, we can make the model much smaller and fit in personal laptops. Pushing more to 2-bit, we can even make it run on our mobile phones. And as I said, since the inference are memory-bound, less model size also means we can do faster. So quantization can make the inference time be up to 16 times faster. And the challenge, of course, is to reduce the model size without hurting the model quality. And this is what our work focuses on. At a very high level, quantization is just a mapping from continuous value to a small number of discrete levels. So here is a simple example of 3-bit uniform quantization with 8 equally spaced quantization levels. However, both the quantization levels and the weight assignments can be non-uniform. There are lots of different quantization schemes. I will touch on the state of the art very shortly. After this mapping, we need to store two things. One is the quantized weights, basically the discrete assignments, and also the codebook or parameters related to quantization. For example, the 8 representative values in full precision. And as in my example, the simplest quantization is just scalar quantization, where we map each weight value individually. And this used to be the dominant approach for model quantization because it's simple, with very fast encoding, decoding, and usually just a tiny codebook. Methods like GPTQ and AWQ can already achieve near lossless 4-bit quantization. However, when we go to smaller number of bits, their performance drops a lot. And more recent work started exploring vector quantization, which I won't get into detail, but they usually achieve better performance in low-bit regimes, however, with much higher complexity, which means they will make inference much slower. So we ask, can we achieve the best of the both worlds? In this work, ICQuant gives an answer, yes. We evaluated our method, ICQuant, on a very wide range of models and benchmarks, but here I just wanted to emphasize some results on Llama 3 70B model. This is a model known to be hard to quantize, and the table here shows the zero-shot accuracies of quantized models. As we can see, just applying ICQuant on some simple scalar quantization method, we can outperform all state-of-the-art vector quantization methods by a large margin. For example, if we look at our around 3-bit method, it can be better than 4-bit baselines. And ICQuant is not just more accurate, it's also more faster. The table here reports the CUDA latency of a standard linear layer. And as we can see, ICQuant is much faster with lower latency than all baselines. Now, before getting into ICQuant, I want to explain a little bit more about why low-bit quantization is a very challenging problem. So a key issue here is outliers, which are the weight values with largest absolute values. In trained large language models, it's known that weights are roughly Gaussian-like distributed. As shown in this figure, the majority of weights are clustered around 0, with a few number of outliers appear in the tails. But those a few number of outliers can inflate the quantization range, making the quantization very inefficient, especially in especially in low-bit region. For example, here is an example of 2-bit quantization, where we have to allocate 2 levels, which are just half of all we have, to just take care of a few number of outliers. And we have to quantize all the remaining values to just 2 values, which would lead to a large quantization error. And this is a problem known for a long time. Lots of quantization suppression techniques have been proposed to fix this problem, but they all have limitations. One example of existing solutions is to keep outliers in full precision. This can reduce the range of the majority of weights and lead to better quantization quality or accuracy. However, it comes at a cost of high storage overhead. We need to store both the outlier values in high precision and their position. So we can only afford to store a very small amount of outliers. Therefore, we ask, can we encode outliers more efficiently? This leads to ICQuant. Our solution is inspired by some new statistical observations about outliers. I will talk about one by one. Yeah, so first observation we found is that 5% outliers take approximately 50% of the total range. As we can see, here is some true weight distribution taken from Llama 2 model. And the yellow part are 5% outliers. The effective range is almost the same as the inliers, which are the blue part. Based on this, instead of quantizing all weights together, we propose to identify outliers first, and then quantize them into the same precision, but using a different codebook. Which means now with 5% outliers, for each part, we can use the same number of bits, but quantize only half of the range. Consequently, we can achieve, as shown here, 3-bit quantization quality, but only store each weight in 2 bits. And this idea can be applied on top of any quantizers. Yeah, and however, this saving is not for free. The challenge here is we need to store outlier positions. A very naive approach is just to store outlier indexes directly. However, the problem is due to the high dimensionality of large language models, we would need at least 16 bits for each position. And for 5% outliers, this is around 0.8 extra bit per weight. This would kill the saving. So can we do better? Here comes our second observation. We found that outliers are actually spread out almost uniformly. We verified this using statistical tests on many different models. Here is just a small example showing the number of outliers in each group of around 200 weights in Llama 2 model. As you can see, they're all around the same level. So based on this, we propose to encode the index gaps between adjacent weights, adjacent outliers, as shown in this example. If the outliers are spread out, the gaps in between is likely to be small and within some range. This would allow us to use much smaller number of bits to just encode the gaps. However, the issue here is there are still some large gaps in practice. So our solution is just to split those large gaps into multiple entries. For example, here we split 20 into 15 and 5. Although this index coding scheme is inspired by the uniform distribution observation, it actually is compatible with any outlier distributions. And the difference is just the storage overhead. So the question is, how many bits do we actually need to store outliers? For the ideal case, where outliers are spread out uniformly, we derived an upper bound on the total storage cost, which depends on the outlier ratios and the data format, how many bits we use to store each value. And the figure here plots the total storage overhead when we use different number of bits to store each value. As we can see, for 5% outliers, the best we can do is around 0.3 bit per weight extra. This is much cheaper than the 0.8 baseline. Also, there are actually 3 almost overlapping lines here. The first is an empirical estimation using a true uniform distribution, and the second one is our upper bound. The third one is an empirical estimation using a real language model, Llama 27B. And the overlapping shows that our upper bound is tight. And in practice, indeed, outlier positions are uniform. Now, what if outliers are not uniformly distributed? We also provided a theoretical analysis on the maximal storage overhead and a very simple solution to make the storage overhead almost the same as the ideal case. But I won't get into detail here. You are very welcome to check out our papers or poster. To give a very quick summary, in this work, ICQuant, we proposed a new post-training quantization framework for low-bit weight-only quantization. It can be applied on top of any quantizers, and is compatible with any outlier distributions with theoretical guarantees on storage efficiency. Yeah, thank you so much for listening. And I'm very happy to answer any questions or for further discussions at the poster.
We have time for one question.
Hi, I'm curious, do you know why the outliers are uniformly distributed?
We don't have a very accurate explanation for that. But one possible reason is that the weight distribution, when we do the initialization for the model, the initialization is already Gaussian. So it's likely the training is just doing some fine-tuning or learning on top of that.
I can ask you one follow-up to that. Do you notice if the uniformity exists for other models, other architectures, other than transformers? Maybe convolution networks, for example?
Apart from transformers, I'm actually not sure. All the models we examined are transformer architectures. Yeah.
Okay. Thank you. Let's thank the speaker.